This is problem 7-40 on page 350. Draw the shear and moment diagrams for the beam A in terms of the parameters shown. And then part B, set P equal to 800 pounds, A equal to 5 feet, and L equal to 12 feet. So the first thing to do is to resketch the system that's given. I like to do this rather than just beginning to solve the problem because it helps me understand the problem, helps me think about how I'm going to go about solving the problem, make sure I don't miss anything. A lot of times I read a problem statement and then I start working on it, and if I haven't drawn it out, I'll miss something obvious, like for example, there are 2 loads P, not just one. Anyway, eventually this will be 800 pounds, so I'm going to go ahead and write that information down now. And the spacing is given the symbol A between, well, lowercase a, and it's ultimately 5 feet. But the overall length of the beam, L, is 12 feet. Now, of course, we're supposed to figure out the shear and moment diagrams in terms of the parameters given, first of all. Now, let's start off with something simple. Start off with a free body diagram. You notice that the setup is symmetrical. And there will, of course, be support reactions on the left side and the right. Now, despite my drawing, let's try that again, maybe more like that. Since this is symmetrical, we've only got 2 loads and 2 reactions, those 2 reactions are going to be equal to each other. You can calculate sum of moments about either end, or sum of moments and sum of forces, but you'll find that R1 and R2 are equal, and that each one is equal to the magnitude of the load P. So I won't go through the detailed analysis of that part. That's not really our focus in this chapter. What I'd like to do instead is help you understand that when we make shear and moment diagrams, what we're really doing, we end up not drawing these free body diagrams very often. It can be difficult for students to understand, but I want to draw them so that you can follow along, and as the problems progress and become more difficult, you understand what's going on. So we're going to make a free body diagram where we've cut the beam here, or somewhere here. I don't care exactly where it's at, it doesn't matter. We will end up with a shear force and a moment. Now I'm just drawing these in the positive directions. Now let's say we cut this beam at a distance x from the end. Okay, so our reference is the left-hand side. What would be the magnitude of the shear load? Well, it would just be R1, wouldn't it? Because we need R1 and V to be equal and opposite so that the body, this little bit of material, this free body, is in static equilibrium. That is required. What about the moment? Well, the moment, if we saw moments about, say, this point here, about the cut, well, then the moment is going to be equal to just x times r1, right? At least that's its magnitude. Now, what direction would it be? Yeah, that's the correct sense, because these two form a couple to rotate clockwise. This, the moment will have to rotate counterclockwise. So this would simply be xv in terms of the shear, or xr1, if you like. Of course, r1 is p, so ultimately this just is x times p. Now that's not the only free body diagram we can take. We can cut the beam anywhere along this length between this pin and load P, and this is what we would get for the loads within the beam. But what if we were to cut the beam after the first load P? Trying to make it all line up. Move these. So this is a separate free body diagram. And all we've done is move the cut over. We still have R1. There will still be a shear force within the beam and a moment within the beam. But now we've got this extra load P. Well, notice that P and R1 are equal, and so the amount of shear necessary is 0. We don't need any force within the beam to keep the beam in static equilibrium in the vertical direction. Do we need a moment? Yes, we do need a moment. If you were to sum moments about, say, this point or this point, it doesn't really matter where, what you'd find is that you'd have the moment of P plus whatever moment there is in the beam. So the moment within the beam would simply be P times A. And it wouldn't depend where you cut the beam. In other words, the moment within the beam varies between this section, the pin, and the first load P. But after P, the moment remains constant, as does the shear. Of course, the shear is actually 0. What happens after we, well, it's going to be similar to what happened before, isn't it? Because this is a symmetrical beam. But let's go ahead and prove it with a free body diagram. So R1 is still over here on the left, it's still equal to P. We've got our two external loads P. And now we'd like to ask the question, what is the shear equal to? And the moment. So what are the magnitudes of those two things? All right, so what I'm going to do is some moments about this point, for example. So I'll have, what, P times A? For the moment of P, that's a negative thing, so I'll have to counteract it. And then I'll also have 2P times A, or in other words, I will have P times, I said 2, I'm sorry, I was thinking the distance between these is all the same, but we don't know the space in here. So what I'm going to do is take L minus A to represent the length out to the second load. And then what else? Well, the shear will also provide a moment, but what is the magnitude of the shear? Well, let's see, it must just be negative P. Because look, we've got one force P up, two forces P down. We better have another force up, but we always draw the positive shear direction downward when we have a right-hand cut face. And so negative P is the magnitude of the shear. In other words, the shear is actually pushing up. So that's going to be an opposite sign, an opposite S-I-G-N. And I've got it as, oh, I know what I did. Yeah, that's fine. So in the direction it's shown, you could simply say plus Vx, but the fact is V is negative P, so let me just put in minus Px. Because you've got to understand, the amount of shear now is the same, but the moment of that shear varies based on how far over we take the cut, x. Okay. All right, can we simplify this down a little bit? Well, yeah, P times A minus P times A, those two terms go away. And then we've got P times L minus X. So the moment is simply P times L minus X. That's the magnitude of the moment within the beam. So it does depend on where we take the cut, X, as to the magnitude of the moment. So the moment will vary just as it did on the left-hand side. Okay, so now let's try to make a shear and moment diagram. In other words, let's not ask the question from statics, what is the load at one point? Let's ask the question, what is the load at all the points along the length of the beam? Well, the shear is pretty easy to draw, and of course, ultimately this will end up being in pounds, but I'll leave it off for now. We know that the magnitude of the shear initially, as we move from the pin over, is simply P. So the shear remains constant until we reach load P. What happens there? Well, right after load P, the shear goes to 0. So let's align this, pull it down to 0, and then the shear continues over at 0 until we reach the next load P. What happens there? Well, there the shear goes down to negative P. And continues on constant until we reach R2. Now notice I did not make a free body diagram for the situation where we finally reach R2, but think about it this way. Once we've reached R2 and that support reaction is applied to the beam, we will be outside of the beam material, and so the shear would have to go to 0. There is no beam there to have shear in it. Another way to look at it is that the support reaction at the end eliminates the rest of the load that the beam had to carry. So there's the shear diagram. What about the moment diagram? Well, we should be able to do something similar. Of course, we're moving along the beam, along the x-axis. How much moment is there at this point? Well, none. The pin can't apply any moment. And so the moment at the beginning of the beam is 0, but then that moment increases. In fact, it's proportional to the distance x, and it goes up to a value of xp. So if the x value we end up getting to before we reach p is a, then the moment will reach a maximum value of simply p times a. Let me put it over here, that'll make more sense. Okay. Because remember, this length here is a. So the moment increases linearly in the beam and ends up at p times a once we reach load p. Now then the moment is at magnitude p times a once we reach p and remains constant regardless of where we are between these two loads p, and so the moment simply remains constant until we reach load p at magnitude p times a. Well, then what happens? Well, let's see. Well, then the moment is equal to p times L minus x. Now if we plug in, let's see, if we plug in x equal to L minus a, well then this would just be PA, sure enough. We get p times a. If we plug in x equal to L at the end here, we get L minus L, which is 0, so we know that at the end, the moment goes to 0. What about between the 2 points? Well, it's just a linear relationship, you see. So we've got p times L minus x. So as x advances, we take more and more from the length, and the moment becomes smaller. So this is just the equation of a straight line, which means that there's our shear and moment diagrams. Now that's not all they asked for. They said if you have particular loads P and dimensions A and L, what would you end up finding? Well, let's plug it in. Let's modify our graphs now. Instead of using symbols, let's use the actual numbers. Well, the load P is 800. The length A is 5 feet. Of course, the overall length, I guess, is, 12 feet? We could do it this way. We could simply say, since we've got an axis, this is 5, and then 12 less 5 is 7. So there's 2 feet in between, despite my drawing. Not to scale, obviously. What about P times A? Well, since A is 5 feet and P is 800, just multiply the two together, and you'll find that the maximum moment is 4,000 foot-pounds. And that's it. Now we've answered all the questions. We've got a proper shear and moment diagram for our beam. Now, this is actually a very standard setup or configuration, and it's called a 4-point bending setup. The reason it's called that is, of course, because there are 4 points of contact where loads are applied to the beam. And the reason for doing this is because the shear and moment come out so nicely. So what happens is you can actually measure anywhere in the central area, and you should theoretically get the exact same moment and shear load.